In this video, we're going to talk about day 1 of 1.4, limits and derivatives. So note that in section 1.3, we first discuss limits in defining the slope of a tangent line. So on this line, I'm going to write slope of a tangent line. So in defining the slope of tangent line, I'm just going to abbreviate that tan line. Okay, the tangent line was the limit of the secant line. So this is secant line as h went to 0. Now we're going to discuss limits in a more general way. We're going to discuss limits as x approaches some number, and then we'll discuss limits as h approaches infinity, and they'll both be limits of some general function. And then after we do that, we're going to go back to limits of a function as h approaches 0. Right now, we're going to work on limit of f of x as x approaches a number. And we're going to do this by using the function below. I have our definition of a limit here, which I'm going to read to you. It'll become clearer as we use it. So the definition of a limit is, let g of x be a function and a number. We say that the number L, so I'm referring to this equation or this sentence below, we say that the number L is the limit of g of x as x approaches a, provided that g of x can be made arbitrarily close to L by taking x sufficiently close but not equal to a. In this case, we write, and here's our word sentence. This is the limit as x approaches a of g of x, and it's going to equal L. Okay, so that's very confusing because it's written in math ease. So we're going to think about it in terms of an actual function that we can wrap our head around. So here is our function. I'm going to darken my function line. There it is. And I'm going to highlight two values, the 4 on the x-axis and the 7 on the y-axis. So this particular function, the function to the right, is f of x equals 2x minus 1. That's that function right there. It's a straight line. And it says, let x approach 4. That is, a under the limit above is 4. So let's write this in terms of the function that we have on the right. So I would say the limit of f of x as x approaches a is some number L. So when we talk about approaching, we approach from the left, and as we approach from the left, we go up to the function and over to get my y. Up to the function, over to get my y. Up to the function, over to get my y, and we go up closer and closer to 4 from the left-hand side. So we are in effect climbing up this function line and then reading over the function line to the y value. That y value is my L. We also try to approach it from the right. Approaching it from the right, I'm coming from this direction. That's the positive direction. Okay, that's higher numbers. When I approached from the left, I came from the lower direction. So that's going to be a negative. So let's go back to the right. As I approach from the right, I read up and over, up and over, up and over, getting closer and closer. And what I'm seeing is, as I come down my function and approximate the y, I am converging on the y value of 7. So that y value is my L. So the limit of the function as x goes to a is 7. And for this particular case, when I evaluate the function at 4, the value of the function is also 7. That will not always be the case. It happens to be the case here. All right, on the next page, we're going to investigate this same problem of function being 2x minus 1 and the limit as x approaches 4 in a table format. Okay, using the table, I'm going to work with the same exact function. And here is our terminology. We're investigating as x approaches 4 in the limit of the function 2x minus 1. Remember, I found out that in the limit it approached 7. So let's use our function, which is 2x minus 1, and the first thing we're going to do is approaching from the right, so from the positive side, and I'm going to use the black to match what I did on the previous page. We're going to take our x value of 4.1, plug it in my function, subtract away 1, and I'm going to get a value of 7.2. Okay, do the same thing. Pick a value a little bit closer. I'm picking 4.01. Subtract away the 1 that you have in the function. And I'm going to get 7.02. I'm going to keep doing that, and I'm just going to write in my numbers I'm going to get. This is 7.002. If I use 4.001, and this last one will be 7.0002. So you can see that I'm trying to converge on 7 when I approach from the right-hand side. Now let's do the same thing from the left-hand side when I'm approaching with lower numbers. And I think I reversed my colors, but you get the sense of it. So if I plug 3.9 into this function, I'm going to end up getting a 6.8. If I plug 3.99, so a little bit closer to 4, into that function, I'm going to end up getting a 6.98. If I plug 3.999, I get 6.998. And if I plug in an even closer value, 3.9999, so close but not quite there, I'm going to get 6.9998. And you can verify this with your own calculator. So what value is f of x approaching as x approaches 4 from both the right and the left? If I were to round both of those values, I would get a 7. Okay, that happens also to be my function value, but more importantly, it's the limit as x approaches 4 from either direction. We can do the same thing with 3, which I'll leave as an exercise for you. Know that it's going to converge on 5, and that'll be the limit as well as the function value. So you should get a 5.2 here, you should get a 4.8 here, and as you get closer and closer, you expect that this is going to get closer to 5, that's going to decrease and get closer and closer to 5, and if you round both values, you would get a 5. So that's how you would evaluate limits algebraically using a table. Let's move on now to the next page of the notes. Okay, in this page, we're going to analyze it graphically, and I'm going to ask for you to squeeze in one more graph in the corner over here. And this is a graph with no issues. So it's just a plain old parabola, and what we'll do is we'll find the limit as x approaches 2 graphically. Alright, so let me just change my color pen. And as x approaches 2 from the left, I'm going to come up the function, and I'm going to come over to read my y values. And then as x approaches it from the right, I'm coming this way, and I'm going to come up the function, or come down the function rather, and read over. So I'm going this way down the function, and I'm converging on a number, and that number will be 4. So as x approaches 2, when the function is y equals x squared, the y value approaches 4. So the limit, and we'll just call that f of x, as x approaches 2 equals 4. All right, that's the no problem case. That's similar to what we did with the table and the other figure that we worked on with a line. So now look at this second case. I want to investigate the limit as x approaches 2 graphically. So from the left, I'm going to approach 2, and the numbers that you want to be able to see is this is 2 and this is 4, but notice I have a hole. So that hole means that my function will not have a value there. In the first case, my function evaluated where x is 2 equaled 4. But in this case, and I think what I'm going to do is let's eliminate, let me go back. Let's eliminate this so we can write other things. Okay, that's better. All right, so we're looking at the second graph. We're studying the limit as x approaches 2. So we'll call that f of x also. So I want to figure out the limit of f of x, as f of x approaches, as x approaches 2, noting that I have a hole in the function. So approaching from the left, I'm coming this way. You are coming up the graph, reading your y values, up the graph, reading your y values, up the graph, reading your y values, and I see that I'm getting closer and closer to 4. Now let's come from the other side. Coming from the right, as I come down the graph in this situation, I'm coming down the graph, reading my y's, down the graph, reading my y's, down the graph, reading my y's. I see that I'm converging on 4. So since I converge at the same number from either side, that is my limit, and I can say the limit of f of x as x approaches 2 is going to be 4. However, the function value, the function evaluated where x is 2, does not exist because of the hole. This hole is called a removable discontinuity. All right, so where there's a hole, that is a removable. Let's see if we can get that to go back up. Removable, whoops. And I can't write the rest of that word. Removable discontinuity. Okay, so it's a removable discontinuity when you have a hole. So I will put discontinuity here. Discontinuity. Okay, so in this situation, the second case, I had a limit, but I didn't have a function value. So now look at our third case. I have a piecewise function. So this is a piecewise function. We talked about piecewise functions before, and I said they show up a lot in calculus. So piecewise is the type of function that this is. All right, so what I see is that as I approach the value, in this case it's going to be 3, so that means this is a 3 here. On my y-axis, I have a value of 3 right here and a value of 4 here. So those will be the most important values. So as I approach 3 from the left, I go up my curve, and as I go up, I read over. Up, read over. Up, read over. From the left, I am converging on 3. Okay, then I'm going to come from the right, and I'm going to come down my curve and read my x values. So coming down my curve and over to read my x values. When I come from the right, I am converging on 4. So since I'm converging on two different numbers, I would say that the limit, and we'll call this f of x2, of f of x as x approaches 3 does not exist. Okay, it does not exist because I have a piecewise function and I'm approaching two different numbers on the y-axis when I approach the x is 3. What about evaluating this function where x is 3? Does the function value exist? Well, I look, I see I have a hole, and my hole is right here, but then I see this is filled in right here. So the function value as x goes to 3 is 4. So in this situation, I don't have a limit, but I do have a function value. Having this scenario with the piecewise function as we do is called a jump discontinuity. So that's a jump discontinuity. And that brings us to our last example on this page, and that's an asymptote. So I see I must have had a rational function. So I want to figure out the limit as x approaches 3. So this is 3 right here in the center. As I come from the left, I'm going to go up my curve and read my y value. Up my curve as I get closer, read my y, continue to do this, and I'm approaching infinity as I read up my curve, approaching 3 from the left. Approaching 3 from the right, as I read up my curve, I see that I am also getting higher and higher, and I'm approaching infinity. So the limit of this f of x function as x approaches 3, since it approaches infinity, in our class we say it does not exist. The limit does not exist because infinity is not a number, it is a concept. So for us, if the limit approaches infinity, we say it does not exist. We do not say it approaches infinity. What about the function value? Can I evaluate this function where x is 3? And the answer is no, you can't. So that function does not exist at x is 3, and that's because I have the asymptote there. So we have 4 different scenarios for you to go back and think about. Sometimes you have a limit, sometimes you don't have a limit. Sometimes you have a function value, sometimes you don't. Go back and make sure you understand each one, and on the next page of the notes, we'll go through the rules that was on the page underneath these graphs. So let's do that on the next page. All right, so things to consider when looking at the graph to determine the limit of the function. Check the limit from the right and from the left. That's what we were doing when we're going up the curve and reading across to the y-axis. If the limits do not approach the same number from the left and from the right, then the limit does not exist. So it has to approach the same number. Or third things to consider, if the limit does not approach a fixed number, and infinity is not a fixed number, then the limit does not exist. Whenever the limit does not exist, you can just write that as DNE, does not exist. So for have a limit exist, you have to converge on the same y value as you approach the x value of the function from the left and from the right. If you don't, the limit does not exist. Okay, now I've picked some additional functions to analyze graphically. So you have the option of putting these in your graphing calculator, but I will tell you that if you did, this graph would approximately look like this. All right, so that's the graph of negative 3x squared plus 2x plus 4. And if this is the 1 value that I want to analyze, let's just say 1 is here, I would approach it from the left and from the right, and I would then read over to what number I am closing in on, and that number happens to be 3. Now, in this situation, the limit, and this is an f of x function, of f of x as x approaches 3, that limit, approaches 1, that limit is going to be 3. The function value, because this is not a complicated function, there's no holes, there's no issues, there's no asymptotes, so the function evaluated at 1 is also 3. So the limit exists, and the function can be evaluated at that x value, and both of those values will be 3. Okay, the next one is a cubic. And so if you would put it in your graphing calculator, you'd see something that looks like that. And if I'm going to evaluate that at x is negative 1, I'm going to approach from the left and from the right and read off of the y-axis as I get closer and closer to 1, and I find that my value that I'm approaching is 2. So the limit from the left and from the right, which is the requirement, as x approaches negative 1, and this function was called g of x, is going to be 2. Okay, this function, g of x, evaluated where x is negative 1, will also equal 2. So the function value and the limit are the same in this situation. Now the next one's going to be different. You should recognize h of x as being a rational function, and rational functions have asymptotes many, many times. So I can see from my rules of asymptotes that I have an asymptote at x equals negative 2. Right? That's my asymptote. My function looks like this, and then again, the second piece is this. So if I want to figure out the limit of h of x as x approaches negative 2, I'm going to see as I approach negative 2 from the left, I will go to positive infinity. As I approach negative 2 from the right, I will go to negative infinity, and therefore, because I'm not approaching a number, my limit does not exist. So this is a does not exist. What about the function itself? If I evaluate the function where x is equal to negative 2, I'm also going to find that that does not exist because it's undefined due to the asymptote. So our last situation, we don't have a limit and we don't have a value. Okay, the next thing we're going to do is talk about the 6 theorems that are used in limits. So I'm going to very briefly talk about them and then refer you to the textbook and then do some very quick examples, and that will end day 1. All right, let's read through some of these. Okay, the limit of a constant is the constant. So that's this one. So as x approaches some number, a constant doesn't change. So I don't have to worry about figuring out a limit. Whenever you have a constant, its limit as you vary h, or x rather, is still the constant. Okay, our next little law, the limit of a constant and a function is the constant times the limit of the function. And this is how they write that. So you're going to just move that term limit in closer to the function, and then you can figure out the limit by taking the limit times the constant that you had. A lot of these things are much clearer when you have an example. So for example, the limit of 7 as x approaches 3 is still going to be 7. Okay, so think about if this is going to be 7, if your function is going to be 7 times some f of x, the limit of the complete function is going to be 7 times whatever the limit of f of x was. If r is a positive constant, then the limit as r approaches some number, you can bring the limit terms in and handle it this way. So it's going to look like that. The limit of a sum is the sum of the limits. So you can just work from left to right, get every limit, and add them all up, kind of like the power rule. The limit of a product is the product of the limits. So get one limit, and if you have to do the product, multiply it by the next limit. And the limit of a quotient is the quotient of the limits, provided that the denominator is not going to go to 0. All right, those are the general rules. Now, it's easier to understand them when you look at some examples. So let's do that next. All right, so here's some application of using the limit theorems. So if you want to find the limit as x approaches 3 of x cubed, you would move the limit wording inside next to x and then cube that limit, and your result would be 27. Because the limit of x, you can just plug in the x. So in this situation, we're just going to plug in our x value right here and cube it, and we have our answer. Same thing here. The limit of a product, so this is a product, is the k times the limit of the x, and then you square the x. So here you're just plugging in a 2. So 2 squared is 4. So this is 5 times 4. And then plus the limit of a constant is just a constant. So the limit of 7 is 7. And that's how I get my 27. Okay, here I'm going to rewrite it one different way. If I take that limit, I should have said, I take the limit of x as x approaches 1, and I square that, and then I'm going to add to it the limit of 8 as x approaches 1. And then once I've done that, I'm going to take the whole thing and raise it to the 1/2 power. So I'm going to look at that function. Because of the nature of the function, I know I'm only going to get the principal root. So the limit of the function as x approaches 1, if I plug in a 1 and square it, so I'm going to get, when I do that first term right here, follow it down, I'm going to get 1 squared plus the limit of a constant is just the constant, that's 8, and then raise that to the 1/2 power, so the square root of 9 is just going to be 3. Now, can we do this next one? The limit as x approaches 5 of 4x squared is going to be 4 times the limit of x squared. So the limit of x as x approaches 5 will be 5. So I have 5 squared, which is 25, times 4, which is 100. So we're going to do the homework, which was listed on the portal, but it's on page 101. We're going to look at 1 to 16 all, and for problems 1 to 6, write a sentence for your answers. For problems 7 to 16, you're going to use the limit theorems just like I used here. So this is the end of day 1 of the 1.4 limits.